Okay, in this video we're going to take a look at our second perspective, which was forces. Now, in translation, we just refer to it as force, but in rotation, we're going to refer to it as torque. In translation, a force, a net force, would cause an object to accelerate in a straight line. Well, in rotation, a net torque will cause an object to accelerate as it spins. So it's not going to be moving through space, it's just going to be spinning on an axis. So torque is the rotational equivalent of force, and torque we're just going to say is a rotational force. That's the easiest way to describe it. Now, when we look at forces in translation, we don't really pay too much attention as to where the force is applied. We just draw a box for an FBD and we put the forces on the box. As long as the tail is on the box and points away from the box, everything is good. Well, that's not going to be the same whenever we look at rotational forces. We're going to have to pay careful attention to where we actually place the force on our diagram. So we will no longer be drawing a box to represent the entire object. We're actually going to have to make a sketch of what the object looks like, no matter how simple the sketch is. It doesn't have to have a lot of detail. It does have to show the approximate dimensions of your object. And then you will place the force, the tail of your force vector arrow, at the location that the force is applied. And we'll see more of this in upcoming videos. But for right now, we're just trying to get an understanding of what torque really is. Now, torque has units of meter newtons. And it's very common to see it written as Newton meters. But we don't like to do that. Can you guess why? Okay. The reason we don't like that is because the Newton meter we said was the joule, the unit of work or a unit of energy. And that's going to cause some confusion because torque has nothing to do with energy. I mean, yeah, you apply a force, and if the object begins to rotate because of the applied force, then yeah, there was a transfer of energy. But it's not the same thing. So the easiest way to keep it straight is to think of torque as meter newtons and not Newton meters. If you work in, if you've ever worked on your car, you might see, especially if you're working on the engine, you might see that the service manual tells you to torque down the bolts to a specific number of foot-pounds, for example. And so in imperial units, foot-pounds would be our unit of torque. Okay, so anyways, let's get away from that and let's continue to talk about torque for a little bit. When it comes to torque, what we're going to learn is that torque is dependent upon not only the size of the force, not only the location of the force, but also the direction of the force or the orientation of it. And we're going to have to use a picture here to make sense of this. Okay, so what I've drawn here is a door, and what we're looking at here are the door handles. That's what these knobs are. This is the hinge, and we're looking down on it as though we're standing up in the ceiling looking down on the door. So the door can swing from this perspective on our screen. The door can swing up or down. So it can swing either this way or that way. Now, when it comes to torque, we say that it depends on the size of the force. Well, let's get away from that for just a second and let's take a look at the other two really important factors. I think the size of the force is an obvious one. But what about the location of the force? Well, if I place a force way back here near the hinge, it's going to be very difficult to make the door open or close. On the other hand, if I place the force way out here on the edge, it's going to open or close without any difficulties whatsoever. And so the further away you are from the axis of rotation, and that's what this hinge is, it's an axis of rotation. The further you are from the axis of rotation, the easier it is to make the force rotate the object. And so by virtue of having a greater distance between the force and the axis of rotation, we have a larger torque, even though the force itself hasn't changed in size. Now, the other thing we have to pay attention to is the direction of our force. If you were to push inwards on the door straight along that axis, the door wouldn't close. It wouldn't open. It's not going to do anything because of the direction that the force is pointing. On the flip side, if you grab that door handle and you start pulling on it in this direction, you're going to meet with the same result. You're not going to cause the door to open or close. Now, on the other hand, if you were to pull on the door in that direction, then it would be possible to make the door swing. And so it's going to open or close, but the force is not going to be particularly effective. Because the force is going to have a component which is parallel to the door, and it's also going to have one that's perpendicular to the door. Now, as we've already established in the two extreme examples, this parallel component right here is not going to do anything towards helping the door open or close. But the perpendicular component of that force is going to help it to open or close. And so ultimately, when we do torque, what we're looking for is the component of the force which is perpendicular to, in this case, the door. So let's go ahead and more formally define what torque is. So, by mathematical definition, torque is equal to R cross F. Now, torque is a vector, R is a vector, and F is also a vector. So, if you recall when we did work and energy, we said that work was equal to F dot S. Just a real quick reminder here, we said work was equal to F dot S, and that this was vector multiplication because force is a vector, displacement is a vector, but work itself was a scalar quantity. So this was called the dot product or the scalar product. Two vectors multiplied together give us a scalar quantity. But we can also multiply two vectors together and get another vector. And that's what we have in this situation. And so we don't need to worry about, what does this X or what does that cross really mean for us? What we're most interested in is the fact that we get another vector out of this. Now, if we are just looking for the magnitude of the torque only, so we're looking for this. We want the magnitude. We don't care about the direction part. Then the magnitude of the torque is just going to become R times F times the sine of phi. So just like when we did work, we said work was equal to F times D times the cosine of phi. We're going to have the same thing with torque. This here gave us the component of F, which was parallel to D. Well, this angle phi also was the angle between the two vectors, so phi was determined by the force and the displacement vectors placed tail to tail, and phi was the angle between them. When it comes to torque, the sine of phi basically all it's doing is it's going to give us the component of F, which is perpendicular to R. So in our diagram up here, let me show you what R is. R is the distance from the axis of rotation to where the force was applied. So this is R. For these forces out here, this would be R. For this little force right here, the force that was in close to the axis of rotation, it would just be this little tiny arrow. And when you look at our equation, you can see why it would take a tremendous amount of effort to make the door close, because R is so small in this circumstance. Because the hinge is the axis of rotation, and the hinge is very close to, but not exactly on top of, the force vector itself. So don't confuse that. Okay, the force vector is some distance r away from the axis of rotation, but it's very, very close, making it very difficult to close that door. Now, phi, just as a reminder, phi is the angle between r and f when those two vectors are going to be placed tail to tail. So in our example up here, I'm going to use this force right here, the one that's pointing at an angle. And so if I draw that vector diagram, I have R, and then I have the force vector that looks like this, and this becomes the angle phi. Now, remember, all that's really doing for us, whenever we do R times F times the sine of phi gives us this component of the force, the component which is perpendicular to R. Okay? Now, that's one perspective on it. We could also look at it as the component of R which is perpendicular to F, and we'll get to that in just a few moments. So we can rewrite our torque equation as torque is equal to R times F perpendicular. Okay, so in concept form, this is what you need to remember. What component of the force is perpendicular to R, because that's what will establish my torque along with R. Can't just look at the force, you also need to know what R is. But the only part of the force that's going to do anything is the part which is perpendicular to R itself. Now, this is how I suggest my students go through it always. However, when you read your textbook, or if you go on the internet, or possibly talk to some of your friends who are maybe even at another school, all right, you're going to be confronted with another perspective on calculating the torque. And that is that you're going to hear that the torque is equal to R perpendicular to F. Now, hopefully you can see from this equation that whether it's R perpendicular to F or F perpendicular to R, it's one and the same thing, because I can do, R sine phi times F, or I can do F sine phi times R. It really doesn't matter. It's multiplication. It can happen in any order. Okay, and so sometimes that's what happens whenever we look at torque. Now, the component of R which is perpendicular to F gets a special name. This name is called a moment arm. And then we just have the force itself. So let's see if we can understand what the moment arm is. Okay, so let's take a look at a situation, and let's just say we have just a rod or something like that. And we're going to put our axis of rotation right here on the end. And we're going to apply a force which is pointing in this direction, just like we had before. And okay, so well, here we go. Okay, so here we have this object that we're attempting to rotate, and all we want to do is calculate the torque. Now, the way we would have done it before is we would say R. I should define this actually. I failed to mention this. R goes from, that's important, from the axis of rotation to where the force is applied. Make sure you write that down because that's a really, really important piece of information. So for our purposes, R is going to go from here to here. And then, of course, F points in that direction. So if we're just using the way I've taught you to do it, you would have R, F, and then, of course, this is your angle phi. Now, when we're doing moment arms, there's also another special term you're going to hear, and that term is called the line of action. And the line of action is basically if you draw a straight line parallel to your force and through the application of the force. If the force were literally an arrow that can only travel in a straight line, it would travel along this line. And so the line of action extends in both directions parallel to the force, and it lines up with the force vector itself. Now, this arrow right here is R, and this is our vector. And when you look at right triangle trigonometry, so here's our right triangle. Our vector is always the hypotenuse. Okay, so my point is that if this is my hypotenuse, I need to be able to draw the components such that I have one component of this vector which is perpendicular to my line of action and one that is parallel to my line of action. So if I draw my components on here, then the force vector is going to have to look something like this. See, I need it to be perpendicular to my line of action. There's perpendicular and here's parallel. Okay, so here's perpendicular. This is called the moment arm. This is R perpendicular, and that's what we are interested in. And so you can use the angle to figure out what R perpendicular is. So this is really more of a conceptual thing, honestly. I would say stick with what we've done before. Go with what you know. I only point this out so you're familiar with it, because you will come across it if you spend any time studying at all. You're going to come across that.